Yes. Now recording is started. So we were here at this point. Electromagnetic yani Hall's effect. Okay. So hopefully it will be yani I will give you a recap and then we will just continue with today's lesson. Okay. The recap was that once a charge carrier, which is the part of this slice, which is basically semiconductor slice or any material, when it is placed in a uniform magnetic field, then the charge carriers will experience a drift, and these charge carriers, which are the positive charge carriers, they will move on this phase. For example, in this diagram, they will drift towards this phase, and the other phase, this one, that will have an induced negative charge. That is why an electric field will be developed between these two phases, ABCD and EFGH. So if you connect the voltmeter between these two phases, ABCD and EFGH, then what will happen? You will experience you will note down that there is some potential difference, and that potential difference is named as Hall's voltages, right? And yeah, this effect is called Hall's effect. This is why, because when the charge carriers are drifted in one direction, they give a rise to the electric field in the slice, and that electric field exert a force on the charged particle. Let's say this is the charged particle, and that charged particle, there would be two forces acting upon. One force will be its electric force, that will be in this direction, and then there will be a magnetic force in this direction. When these two forces will become equal and opposite to each other, then there would be a constant voltages developed across the slice, and they are named as Hall's voltages. And here there are some points, some properties, yeah, dimensional properties, that T is the thickness of the slice, that is the side which is parallel to the magnetic field, and T is the breadth of the slice, and that is parallel to electric field electric field line, and L is the length of the slice, and that is parallel to current, right? So these all points are very important. So here is another diagram. So working principle, I told you that when electric field and magnetic field would be sorry, when when a charge carrier enters in a uniform magnetic field in a conductor or in a slice, it is drifted in one direction, and due to that drift, there is there is an the one side or one face of the conductor becomes positively charged, and the other becomes oppositely charged and negatively charged. That is why an electric field is developed across these two faces or between these two faces. And when that electrical when and that causes an electric force on the charged particle opposite to the magnetic force, and when these two forces becomes equivalent opposite, the charge moves undeviated, and a constant voltage is evolved across the space. This causes a potential difference across the phases. Constant voltages are potential difference across the slice. Okay. And here that potential difference was called the Hall voltage. That is the summary. And today I was about to tell you about how to derive this Hall voltage. So are you people ready? As I told you that the equation of Hall voltages was VH is equals to IB divided by NQT. Now here V Halls are the Hall voltage, I is the current in the slice, B is the magnetic flux density, N is the number density, and Q is the charge of the one charge carrier, and T is the thickness of the slice. Right? So here These all notations are very important to write. V, I, B, N, Q, and T. And these all are asked to you one by one. Yes. So what was this VH? VH is Hall voltage. I is current in the slice. B is magnetic flux density. Magnetic flux density. N is the most important. N is number density. Number density. You will be asked about this. Number density mean number of free charge carriers per unit volume. Number of free charge carriers per unit volume. Carriers per unit volume. Okay. Then Q is the charge on any of the charge carriers. Charge of any charge carrier. And T is thickness of the slice. I mentioned it above. Thickness of slice. Now, what will happen if you are yeah, Hanzala did not join the class yet? Oh, okay. Sorry, Hanzala, are you there?
Yes, sir.
सॉरी यार मुझे मैसेज कर देते तुम के वेटिंग पे हो.
कोई नहीं, ज़्यादा देर नहीं था वहाँ।
Okay, okay. So basically, till this point, we have discussed only this area, that what is V, what is current, what is I, B, N, Q, T. Now, for the derivation, we will start the situation that, okay, as you know, that from the concept of velocity selector, the velocity of the charge part, sorry, rather than this, I will start right from which point? The point of equilibrium. In case of equilibrium, in case or at the stage of equilibrium, what will happen? F electric will be equals to F magnetic, and this is equal to E times Q, and it is equals to Q V B sine theta. Theta is equals to 90 degree. That is why your equation will become Q V B. Okay, what will be your equation then? Your equation will be EQ will be equals to QVB. Now this Q and Q will be cancelled out, right? This will be gone. Q and Q is gone. So what equation do you have now? That is E is equals to V times B. But here I will not write in this way that yes, according to the velocity selector, the velocity is E by B. No, that means that I need some different criteria, or I need some different parameters. That is why here, as I mentioned earlier, that the charged particles experience a drift. So this is your drift velocity, which is equals to I divided by N E A. Lulu, isn't it the same formula for drift velocity?
Yes,
Is this
sir.
the formula? Yes. I divided by NEA. Okay, so that will be replaced here. That means that E is now equals to this V is replaced by I divided by NEA, and this B will be written as it is. So it means that this V is basically that has been replaced by this, the black color matching Then this E is equals to, delta V divided by T. Is it clear to everyone? And this equation will become IB divided by NQA. Why I have switched this E? Because E can be equals, E is sirf electron. Is it? E is electron only. But Q can be positive charge carrier or negative charge carrier depending upon the situation. So that is why we will prefer to write Q other than V. So is this clear? So here delta V is your Hall voltages, that is your VH. So you can simply replace these all notations. So you will write now that VH divided by D is equals to IB divided by NQ. Now I will stay here for a while. As I told you that when we talk about the phases of the slice through which we were producing the current and we were providing the current, and that current was, for example, yeah, if you remember, I will just draw a small slice here, right? This was the slice now, this way. Thanks. This was the slice. So in that slice, did you notice what were these values? What was this? If the magnetic field is parallel to yani this area, or okay, let's say I can mention these points, and this is the length of this slice. So simply speaking, this was the length, and that size, yani this small side and this breadth. These are two different points. Yani this can be D, this can be T, but this can be L. If I say that what will be the area of this slice? So what will be area? Yes. What will be area? Yeah, yeah. Area
Yes,
is
sir.
this space. Area of the slice is this is the area of the slice. Wow. Is it clear to everyone? This is that area. Okay? Is this clear to everyone or not? This is the area of the slice. Are you
Correct.
getting my point?
Yes,
Yes,
sir.
sir.
Okay, so that is basically that area through which the current is passing. So I can simply say that area will be equals to D times T. That, just to tell you, or just to deliver you this concept, I have drawn this diagram, that it is D into T, isn't it? That is basically the area of the slice. Got my point? Is it? Should I move on? Now your D on this side and D on this side is cancelled out, and you people got the value of Hall's voltages as V Hall's is equals to IB divided by NQT. Is this clear to all?
Yes, sir.
Confirm clear? So that is why I prefer this entire concept, that the derivation will be asked to you. This derivation is usually of 2 to 3 marks, not more than that. But it needs your detailed concept. Dekho, you people will not be asked to write each and every detail along with this derivation. What are the main points where uh, you people will just uh, Yani for exam prepare. For example, this is an exam derivation, right? This is an exam derivation. Okay, for exam derivation, you will write f b equals to f e or vice versa. You will write q v b, and that will be equal to e by e into q, and from here you will cut the q's and you will replace the values, that it is equal to I divided by n q a and into b, and that will be v halls divided by d. You will simply write in this way, and in after one step it will be your derivative, yani your desired equation. You will write t into d or d into t equals to v halls divided by d. So then you will cut this d and d, and finally you will get this. Is it clear to everyone? So this is your exam derivation, because I'm just explaining to you. That is why I have put more details. So here you have shown this equation, that yes, V halls is equals to IB divided by NQT. So any confusion or anything which is not clear to you from my side? Yes.
No, sir.
No,
Is it clear to
sir.
everyone? Okay. Now there are some quantitative analysis. No, sorry, qualitative analysis of this equation. The qualitative analysis are uh, here. This Hall's voltage is basically directly proportional to what? That is directly proportional to I. That is Hall's voltages are directly proportional to P. Hall's voltages are inversely proportional to number density, and Hall's voltages are inversely proportional to thickness of the slice. So this is another very important thing to discuss, that these points are important and you have to keep all these points with you, that basically where the house voltages are there and which are the factors upon which they depends. Now that is why you people are asked about several questions, right? From here, if I want to calculate the actual, what was the main objective of Hall's voltages? Objective of Hall's voltages was to figure out the magnetic flux density. That is why if you just figure out, okay, how will you figure out or how will you find the magnetic flux density, then your magnetic flux density from this, that will be equals to, yes, that will be equals to value of Hall's voltages divided by current in the wire into NQT. Why I put all these numbers in the brackets? Can anybody tell me? Basically, you need a voltmeter with the help of which you will note down the voltages, Hall's voltages. And you need only an ammeter through which you will note down the current reading. Rest N, Q, and T, they are basically the physical properties, or they are the constants to somehow. Okay, but it depends upon the choice of your choice. N is the material. I will explain it, and T is the thickness. Right. While selecting the Hall's probe, there are several points to note down. Okay? While selecting a Hall's probe, two very important things. One, metals are not preferred. Okay? And semiconductor materials are preferred. Metals are not preferred. Semiconductor materials are preferred. You can ask me a question. Why? Because, yes, yeah, yeah. Can you answer this question?
Yes.
Yes. Why?
Um, sorry, I forgot.
Because Hall's voltages are inversely proportional to number density, right? And metals have, this is the past paper question actually, 2 marks explanation. Metals have significant number of free electrons or number of free charge carriers, number of free charge carriers, okay, per unit volume, per unit volume. So the Hall's voltages are not significant. Is it clear to everyone?
Yes, sir.
With
Yes, sir.
metals, when you use the metals, they will not be significant. And otherwise, for semiconductors, N is less. Okay. For semiconductors, N is very small or very less. So V halls are significant. Any question till this point? Second thing, if you have selected semiconductor materials, the semiconductor materials are of two types. Semiconductor materials are of two types. Okay. One in which they carry the positive charge carriers, they carry the holes or charge carriers. They're called P type materials, right? What do we call them? P type material. ठीक है? And the second ones, they are negative charge carriers, yani electrons are charge carriers in them. That is why they are called N type material. What do they what do we call them? N type material. So these N type and P type materials have different types of charge carriers in them, but you can use both the materials for the Hall's probe. For example, if a Hall's probe is of that contains the positive charge carriers, then what will happen? And if a Hall's probe contains a negative charge carriers, then what will happen? So instead of trying a Hall's probe again, let me place this here and let me explain the concept to you. Okay. So these are two Hall probes. In one, the charge carriers are positive, and in the other, the charge carriers are negative. You got my point? Hmm. Okay. Okay. My question is very simple. This is your T and this is your T. It does not matter. I have changed the situation according to requirement. Now, the uniform magnetic field is from top to bottom. As I told you, that there is a uniform magnetic field in this region. Same goes here. A uniform magnetic field is from top to bottom on this semiconductor as well. So, what do you think? What will happen? Where would be the positive charge carrier drift, and where will be the negative charge carriers drift? Yes, Hanzala. You will explain me the direction of motion of the positive charge carriers. Yes. Okay, wait. It would be quite easy for you if I just reverse the situation. Just a second. Sorry. My apologies. That diagram, the title was very true. That was D, that was D, that was D, that was D. Okay. The magnetic field is into the page, right? Now is it clear? The magnetic field is into the page for both of them. So rather, yani, instead of drawing the lines, the magnetic field is into the page. Okay. Where is the magnetic field? Uniform magnetic field is into the page. Now, Hanzala, tell me please, what would be the direction of motion or direction of drift of positive charge carriers? Yes, Zoya, can you tell me?
Third down.
Downward? Yes, डर के क्यों बता रही हो? Yes, you are right. The positive charge carriers will drift down on the lower face. Is it? So positive charge carriers, they will drift down on the lower face. So in that, yani, in this way, this face becomes positive, lower face becomes positive, and what about the upper face? That will become negative, na? Hello, are you people getting it?
Yes, sir.
Okay. अब देखो, if the lower face is positive and the upper face is negative, then what about the other diagram? Okay. Okay, wait. If I want to connect the voltmeter here, what will be the value of yani? Oh, sorry. Right? I'm just connecting a voltmeter. So voltmeter will give you certain values. Is it? So what would be the voltages, or you can say whether the polarity of the voltages, let's say I'm just considering a simple value. For example, you have connected a voltmeter, a digital voltmeter. and that digital voltmeter is giving you positive 0.2 millivolts. Got it? Are you getting my point?
Yes, sir.
Hello,
Yes,
is this
sir.
clear? Okay, the drift of the charges was downward, but voltages are, let's say, plus 2 millivolt. Now, here, if I connect a voltmeter across this, uh, uh, sorry. First of all, let me now from you that what would be the drift on these negative charge carriers on this uh, slice? Hamzala, are you there? Lulu, can you tell me, please?
Sir, please may you repeat the question?
I'm saying that what would be the direction of drift of these negative charge carriers?
Sir, I think to the right side.
Okay, just see this diagram and then tell me. When a positive charge carrier was entering, it was drifting downwards. Now there is a negative charge carrier entering. So what would be the drift of this charge particle?
Sir, to be drifting upwards.
Yes, exactly. So this charge particle will be drifting upward. So drift is now reversed. Did you notice? What is the drift? Drift is now reversed. So this phase becomes negative, and as a result, the other phase is having a positive charge induced on it. You got my point? Is this clear to everyone?
Yes, sir.
Yes.
Okay, so now if I connect a voltmeter again here, what is your idea that what will happen to that? Yani, what will be the reading on this voltmeter? Can anybody suggest me the reading on this voltmeter? Again, this is a digital meter. Yes. Hurry up. I need a logical answer from many of the students. Very genius students are there in my class. Yes, all genius students. Hello, everyone. I'm just playing with my diagram. I am giving time to you. Yes. My question is not that type of horrible question, basically. My question is very simple. If the voltages are 2 millivolt, 0.2 millivolt, my question is whether they will be positive or negative. That's the simple question I have.
Sir,
Such
it's
a simple
negative
question I have.
0.2.
Yeah. Will they be positive or negative?
Negative.
Negative, sure.
Yeah.
Okay. Anyone else who have some different opinion or different type of conclusion? Yes. Hurry up. Okay, I can give you a chance to give me answer of this question. For example, if you have a battery, right, and you are going to connect a voltmeter to that battery. This is a battery. Okay. Okay, students, this is a battery, and you are going to connect a voltmeter with this battery. So, what do you expect if I connect the voltmeter with this part of the battery, and that voltmeter, you are expecting that this voltmeter is reading how much? 0.2 millivolts negative, sorry, positive, 0.2 millivolt positive. Okay, positive 2 millivolts, 0.2 millivolt. What about the what about the next? Yeah, the other voltmeter. Yes. What do you think? I have connected another voltmeter. Do you see this diagram? Is that diagram clear to everyone?
Yes, sir.
Yes, yeah, yeah. What will be the value of the voltmeter here?
It's mechanical.
Hmm?
Nano.
No idea?
Same?
Same, same. Same, same. Guys, same. Do you think that because you have not changed the terminals, you have not reversed the terminals? You got my point.
Okay.
Is it clear? But if you have reversed the terminals in this situation, let's say there is another situation here, you have reversed the terminals. Those terminals are basically reversed in such a way that now this is one of them is yani this is now positive terminal and this one is now negative terminal. Then what do you expect? Hmm? What do you expect? The values should be negative or positive? Hello everyone, yeah. Why you people are not getting clear of that? I mean, I'm just referring this diagram number 1 with diagram number 2 and diagram number 3 with diagram number 4. Yes. Is there any confusion in this diagram? This is negative, this is negative. You got this point, everyone?
Yes.
Yes, sir.
Now, my question is still there. Check this one out and answer my question. Yeah, yeah.
Yes, sir.
Better expecting from you.
Yes.
Yes.
Not exactly.
You're not getting exactly?
Yeah.
Oh my god. Yes, Zoya. The time is very short. I have to manage something else as well for you. Just hurry up, hurry up, hurry up. The diagrams are very obvious, very clear. In both the diagrams, upper part is negative, lower part is positive. So, should they not have same sign?
Okay. Oh,
Yes, they must have same sign. So that shows that when you have reversed the charge particle type of charge particles, yeah, type of charge carriers, the drift is reversed, but the polarity of the Hall's voltages is unchanged. Is this very clear to everyone or not?
Yes, sir.
Better, this is a question asked to you in your one of the past papers. So when the material is changed, or when the material is reversed, or when the material with positive charge carriers is reversed, sorry, replaced, not reversed, replaced with a material with negative charge carriers, then there are 2 points. I want to write that in the form of points. The drift of charge carrier is reversed. The drift of charge carrier is reversed, but polarity remains unchanged. But polarity of all voltages is unchanged. Or instead, you can say same. Is this clear to everyone? So this is the complete description of my Hall effect. I have left nothing, not a single point which I have, which I am expecting that can be asked to you, and I have not explained. Okay, so is this very clear to everyone?
Yes, sir.
Okay.
Yes,
Any
sir.
question? Any question from you? Yeah. Any question?
No, sir.
No, sir.
Okay. See you then, inshallah. And Lulu, you will just